Alright, in this video we're going to be going over a proof of correctness on AVL trees. So what that means is, we've talked about how to do insert and how to determine if the AVL condition is broken and then how to fix it if it is. So what we're going to do in this video is convince ourselves that doing all of that maintains the AVL conditions of the entire tree. Before we get into that, let's remind ourselves of what these trees are for. So remember, trees are to look up stuff fast. So if you need to search something via a key to retrieve data, AVL trees are very good at doing this fast, in all trees. So let's say that you have a tree that has 2 million nodes, and we call search. What is the number of key comparisons that search has to perform in the worst case scenario? So we know that binary search trees have log n performance for search, insert, and remove, and AVL trees maintain that big O because they maintain the balance. So binary search tree only has that if the tree remains balanced. So in order to find out how many, we would just go ahead and calculate log base 2 of 2 million. And when we do that, we get 20.93, so 21 key comparisons, which isn't bad. So remember that trees are used to maintain these large databases and be able to look up into them quickly. So one example of so many is how Amazon would be able to keep track of so many products. The way that it's possible to do that is by putting the data inside of a tree, which reduces so much of how much you need to search because it's only based off of the height of the tree. So again, let's say that the tree has 2 million nodes and we insert into the tree. What is the worst case number of rotations that need to be performed in order to rebalance the tree when insert is called? So we know from last time that the whole approach to insert is that you search through the tree to find where to insert. Then you walk back up the tree to update the heights and determine if the AVL condition was broken at any point along the way. If it is broken, then you need to determine whether you need to perform one of the 4 cases of rotations. And 2 of those cases have 1 rotation and 2 have 2 rotations. So worst case in any call to insert is that you'd have to rotate the tree twice, a subtree twice. So what we're looking at in this video is that all of this is happening within the subtree. So you find out where your AVL tree is broken, and then you determine what case it is, and then you do a bunch of rotations. But you're not rotating the whole tree, you're rotating a small portion of the tree. So we know we've already gone through, like, in great detail how to update the heights and how to update the pointers so that everything gets fixed, and we're convinced that those are all updated properly. But this is now having us think about, well, what happens to the rest of the tree? I've showed you in examples when I've done rotations that the rest of the tree is unaffected, but can we say that generally? So the general approach we're going to take to proving that when we rebalance a subtree that has been broken, that it doesn't affect the rest of the tree, is that first we're assuming that to start off we have an AVL tree. That's really important. Then we're going to call the height of the subtree h, or any value, any variable. We're going to insert, update, and rotate that subtree, and we are going to check after we do those updates that once we are done rotating, that the height of the subtree is back to h. And if we've done that, then we can convince ourselves that the AVL tree is still an AVL tree. So to do this, let's take the tree that's shown here. And again, we're just going to start naming things. So we're going to call the height of the A subtree within the subtree that we're rotating h minus 1. To get us started thinking about this, the question is, what do we know about the height of B if we are determining that the height of A, or if we're saying that the height of A is h minus 1? So the answer to this is because we know it's an AVL tree, we know that the height of B has to be within 1 of the height of A. So the height of B has to be h minus 2, h minus 1, or h. So what we're going to do now is we're going to go through all of the components of a rotation, and we're going to determine what the heights are of each component generally. And this is for a particular type of rotation, so you can basically repeat this process for all 4 rotations, which we won't do, but this will allow us to convince ourselves. So if we know that before the tree is rotated, that n's height is this, and then we check it after the rotation that it's the same, then we can say that our AVL tree is maintaining its, through its entirety, the AVL condition. So we're going to start off with A being h minus 1 before insert, and then we're going to insert into A, so it's going to go into the A subtree. And so when it does that, we know that after, the height of A is going to be h. We're also going to assume that we're using this particular case of rotation where it breaks at n, so that's another piece of information we know. So we're going to go through and determine all the heights of the rest of the components. So we're going to start with L because it's the easiest, because L is based off of A. So if h is a minus 1 before insert, then L is going to be h before insert. And then if after insert A is h, then after insert L is h plus 1. Next we are going to do C. So C is C can be figured out based off of L. So L is h before insert, right? So because it's an AVL tree, we know that C needs to be satisfying the condition before, and then it needs to be dissatisfying the case after. So this one we can do the after first. So if we know L is h plus 1 after insert, and we know that it's broken at n, then we have to say that C is h minus 1 because we know that it had to have broken. And so it couldn't be h because then it wouldn't be broken, and it couldn't be greater than h plus 1, and then it also couldn't be less than h minus 1 because then it would have been broken before insert. So C doesn't change before and after insert, so because we know it was broken after insert, we can say it's h minus 1, and then we know what it is before insert as well. Okay, so the next one we're going to do is B. B is the trickiest one. So in the last slide, we determined that B would either need to be h minus 2, h minus 1, or h, and we know it's one of those 3 options just because we know that before insert it's an AVL tree, so B has to be 1 away from A. So now we just need to kind of try each of them and see if any of them make it so that it's not true. So we're going to start with h. So if B is h, then one of the things that we know, I'm going to use a different color. Just got rid of my subtitles. So if B is h, then L actually would have to be h plus 1, right? And so then after insert, so if B was h, then L would have to be h plus 1. And then if L was h plus 1 and C was h minus 1, then before insert, this wouldn't be an AVL tree, right? Because those are greater than 1 difference. So that means that B cannot have height h. Okay, so let's go back to red and go back to what we had. So L has to be h, and B cannot be h. So now let's try h minus 2. So h minus 2 would mean that B is h minus 2, and then let's see, so if B was h minus 2, then after insert, it would be the same, right? Because insert doesn't change B, so it would also be h minus 2. But then you could see here that this has a greater than 2 difference, or greater than 1 difference, and so this would mean that our AVL tree would actually break at L, not at N. So we know that it can't be h minus 2 either, because then it wouldn't break at the right spot. So that leaves us with B has to be h minus 1. B doesn't change after insert, right? Because it's not affected by the insert, so it's h minus 1 on both sides. So now we can get N. That's the easy part. So N is going to be 1 plus L. So N is going to be h plus 1. And then it's after insert, it's going to add 1 too, so it's going to be h plus 2 after insert. Okay. So we can generally say that for this particular case, that the height of the subtree that we're rotating around is h plus 1. So we can draw out these heights on our tree here before and after insert. So we're going to do this just generally. So we have h minus 1 is the height of A. H minus 1 is the height of B. L is H. And then N is H plus 1. C is H minus 1. So that's what it is before insert, and then after insert, we're going to have A be H, B stays at H minus 1, L is going to be H plus 1, N is going to be H plus 2, and C doesn't change. So that's what we just determined is the only possible scenario of how this particular tree can generally be in terms of height. So there's no other option. So if you insert into the A subtree, which forces a left-leaning tree and a right rotate, this is the only scenario you can have before and after rotation, which we just showed generally. So now what we're going to do is put those heights that we just determined after insert onto our tree and check what they are after rotation. So we found that after insertion, the A was H, the B was H minus 1, and the C was H minus 1. So I'm just rewriting what we wrote here onto the pre-rotated tree. That means that L is going to be H plus 1 and N is going to be H plus 2. So what does it look like after rotation? So we showed last time that after you rotate, the heights of A, B, and C don't change. So A, B, and C are still going to have the same heights, but N and L's will change. So N is now going to be H, and then L is going to be H plus 1. And as you know, we're going to relink the parent up to L, and it's going to become the new subtree. So what we found is that before the height of the subtree, before insert, the height of the subtree was H plus 1, and we went through that carefully. And then after we inserted and rotated, we showed that the height of the subtree is still h plus 1. So what that means is that because the subtree maintained the same height, before and after insert and rotation, then we know that if we had an AVL tree before, then we have an AVL tree after. And so that is our rough proof of correctness. It's not a formal proof, but it's a pretty rigorous proof to show that the AVL tree for this particular case maintains the AVL condition at every node. Now, of course, you would need to do this for all of the different rotation cases, which you can do and show that this is the case. So that is it. Thanks.